Okay, welcome to 1.4 Velocity and Acceleration in Two Dimensions. So, last lesson we looked at displacement in two dimensions, now we're looking at velocity and acceleration. So, just like in displacement, velocity can change in size or direction. And it's important to remember that any change in velocity causes acceleration. And that means that even if it stays the same speed but changes direction, there is acceleration happening because it's changing direction. Any change in velocity. Okay, so to get average velocity, we have this formula that you've seen before, displacement over time. Now this displacement, where displacement is the total displacement. So if the journey has a few different pieces, we need to get the total displacement first before we can find the average velocity. And we're going to use what we learned in the last lesson to do that. So remember, total displacement is displacement 1 plus displacement 2 ... You just add all the displacements together. And for this, we use our components method. If you prefer using a different method, that's okay, but in the examples I'll be using the components method to solve this. Now, one little note here is that that's how we find total displacement. To find the total distance, it looks similar. Distance 1 plus distance 2, ... Notice that it's not just the magnitude of the total displacement. They're actually going to have different values because the displacement has different directions, and some of those displacements will cancel each other out. So our total distance will probably be a larger value. And this is important because we use the total distance for average speed. So we'll look at that distinction in the first problem here. We're going to do the average velocity and then the average speed. So this problem says that a family drives from St. John, New Brunswick to Moncton. Assuming a straight highway, this part of the drive has a displacement of this much, and it takes that long. I'm not going to read all the numbers. From Moncton they drive to Amherst, Nova Scotia, and the second displacement is that much. It takes that long. We want to calculate the average velocity of the family's vehicle. So, we have our equation. Average velocity is equal to displacement over time. And we know that our time is 2.5 hours total. It was 1.5 plus 1. And our displacement, we need to add these together. We've got displacement 1 plus displacement 2. We learned in the last lesson how to add displacements. So we need to draw our crosshairs here. And we can draw each of our vectors. So the first displacement is 135.7 going up this direction, 135.7. And our angle here was 32.1 degrees. And our other one was 51.9. And our angle was 25.9 degrees. Now, to add these together, we're going to break them up into their components, where we have our x and y components. And we add the x components together, displacement 1x plus displacement 2x. So looking at displacement 1, this guy, you can see that the x component, we're going to be using the cosine ratio because we have our angle and we're talking about the edge adjacent to our angle. I'll just clean that up a bit there. Okay, so we're going to be talking about 135.7 cosine 32.1 degrees. And that's in our positive direction. It's facing right. So we'll do the second one, which is also positive, 51.9 cosine 25.9 degrees. Good. This gives us a result of 161.64 kilometers east. And now we can do displacement y. Okay, so again we just add them together, displacement 1y, displacement 2y. And now we're using the sine ratio. Now this first one was positive. The second one is negative, it's pointing downwards. So we need to make sure that we're doing that correctly in our math. So we have here minus 51.9 sine 25.9 degrees. And this gives us an answer of 49.44 kilometers in our positive direction, which is north. Good. So we're a large part of the way done now. We have our x displacement and our y displacement. So we can draw now a triangle that represents this. We have x, y, and the total. Looks something like this. Okay, so our x displacement was 161.64. Our y was 49.44. This is for our total. This gives us our total displacement, and we need our angle theta. So there's two more pieces that we still need to do here until we get our final displacement. So the magnitude of our displacement is, using Pythagoras, we've got 161.64 squared plus 49.44 squared. That's using the x and y components of that displacement. And that gives me 169 kilometers. Good. So now we need theta, the angle, and this is going to be using the tan ratio. So we have tan inverse of the opposite, 49.44, over 161.64. And this will give us 17.0 degrees. So that means that I can put over here, therefore, the total displacement is equal to 169 kilometers east, 17.0 north. That's our total displacement, but we're not quite done. We need to get the average velocity. So, one last piece again, remember that the average velocity is equal to displacement over time. So we can put this 169 over our time, which is 2.5 hours, kilometers per hour. And this gives us 67.6 kilometers per hour. Our direction is the same as the direction of the displacement. And there's our final answer. And there you go. That's how we can solve this sort of a problem. So you can see that it was really necessary to add the displacements together first to get this solution. Okay, on the next page, a much simpler piece of the problem says calculate the average speed of the family's vehicle. So now we're not interested in direction or anything, we're just looking at speed. So again, we have average speed is equal to delta d over delta t. And we really need to do this again. We need to add the distances together. So distance is equal to 135.7 kilometers plus 51.9 kilometers. And this gives us 187.6 kilometers. That's our total distance. Our total time is 2.5 hours. And now we can get our average speed. So V average, we said it's delta D over delta T. 187.6 over 2.5 hours, and this gives us 75.0 kilometers per hour. Okay. And now it's important that you see 75.0, that is a faster speed than just the magnitude of our velocity. And it's important that you see that they're two different results. The reason is that for speed, we're not interested in what direction it's going, so the directions don't cancel each other out. Whereas for velocity, there was some canceling out because the directions weren't all in the same direction. Okay, so the last piece here says, could you have solved this problem differently? Could you have calculated the velocity of the first part of the drive, the velocity of the second part, and added them together? Well, let's just look at the problem again. The first part of the journey took 1.5 hours long. The second part took 1 hour. So if we just found the average velocity for this part, the average velocity for this part, and averaged those two together, we would get a different result. It would not give us the right answer because the time for those two parts of the journey wasn't the same. So we can't just take the average. So that just shows you that it's very important that you are getting the total displacement first, not trying to get the average velocity for each piece. Okay. So the simple answer to that question is no. You need to get the average displacement first. Or sorry, the total displacement. So we need the total displacement first. Good. Okay, so that is finding the average velocity, and that's a very important skill. Now, we're going to briefly look at an idea called multiplying vectors by scalars and subtracting vectors. And the basic idea here is that all of our vectors, displacement, velocity, etc., we can multiply a vector by a scalar to change its magnitude. Remember, magnitude is just another word for the length. So we can make the vector longer or shorter. And some examples of that, we could say that b is equal to 2a, or we could say in general that b is equal to ka, where k is just any scalar. So we can take the vector a, and if we multiply by 2, then b will be twice as long. Now, one interesting thing to note here is that if 0 is less than k, which is less than 1, so if k is between 0 and 1, it shrinks a. So if I'm multiplying a by 0.5, I get a vector that's half as long as a, and hopefully that makes sense. Now, when we want to subtract vectors, which is going to be important in the next couple of problems that we do, when we want to subtract vectors, what we actually do is we write it like this. We can say that a minus b, well, that's equal to a plus negative b. And we do this because it's a lot easier to just make b negative than it is to have a formal definition for subtracting vectors. So one last way of looking at this is we can say it's a plus negative 1 times b. So we're doing some scalar multiplication here where we're multiplying b times negative 1. And the idea here is that we basically just flip the second vector backwards and then we add them. That's how we can do vector subtraction, is we actually just flip the second one. So if that wasn't clear, we're going to do an example so that you can see exactly how that works. So here we're saying, in the diagram to the right, we have a car with an initial velocity, 60 kilometers north 20 east, and the final velocity, 60 kilometers north 20 west. We want to find the change in the car's velocity. So we want to find how the velocity changed. Change in velocity, delta v. This is Vf minus Vi, which is equal to Vf plus negative Vi. Okay, and before we go any further with that, I'm just going to draw a picture of what's going on here. We have Vf, this is 60 kilometers per hour, north 20 west. Vi looks like this, and I'm just going to here clean this up a bit. This one is Vf, this is Vi, and if I want to get negative Vi, it's going to have the exact same length, but pointing in the opposite direction. So you can see that this will be 20 now, and this is negative Vi. So what I want to do for this problem is I want to add negative Vi plus Vf. And this, we're not going to use at all. So that's the idea here. So Vf plus negative Vi. And so you can see that Vf is going to be 60 kilometers per hour north 20 degrees west. And then we're adding it to negative Vi, which is going to be 60 kilometers per hour south 20 degrees west. I've got the picture of what that looks like to the left here, so we can actually just start breaking this up now. We have delta V, the x component of this result. It's going to be equal to, well, I'm going to break these into components. My components are a bit backwards now because I have my angles on the other side from where they were before. Before I had angles down here, now I have angles up top. So let's see. The x component here for this first piece is negative, so we're going to say, well, I'm going to say it's positive in the west direction. So this is going to be 60 sine 20 degrees. And the second one is in the same direction, so 60 sine 20 degrees. That gives me an answer of 41.04 kilometers per hour in the west direction. Delta Vy, you can see that I have now 60 cos 20 degrees for Vf. That's going upwards, and then the other one is going downwards, so I'm going to be doing a subtraction. So minus 60 cos 20 degrees. You can see that they actually just cancel each other out, and we get 0 kilometers per hour. So therefore, delta V is equal to 41.04 kilometers per hour. And I'm going to change that actually because we just want 2 digits on this. So 41 kilometers per hour in the west direction. That's how the velocity has changed. And there we go. That's what that sort of a problem looks like. Now, on the last page, we're going to talk about acceleration in 2 dimensions. And for acceleration, we're going to need to use what we just learned about delta V. Because our definition here is the average acceleration is delta V over delta t. So you can see that we need to know how to subtract those velocity vectors. So, to summarize what we did before, our net velocity delta Vx, so we break up the x and y. So it's Vfx minus Vix, Vix delta Vy equals Vfy minus Viy. So you see that we do x and y separately, then we can get the magnitude of delta V, the square root of delta V magnitude is the square root of delta Vx plus delta Vy, and both of those are squared. And theta is equal to the tan inverse of delta Vy over delta Vx. So that's just sort of summarizing what we were doing on the last page there. Okay, so this last problem here details some acceleration problem. I'm going to talk you through the basic idea of it, but we're not going to solve it together. I'm going to leave this for you to solve. But it says that a car turns from a road into a parking lot and into an available parking space. The car's initial velocity is 4 meters per second east 45 degrees north. So I'm going to just sketch this quickly here. Initial velocity is this direction, 4.0, 45 degrees. Okay, the car's velocity just before the driver decreases speed is 4.0 meters per second east 10 degrees north. So now we have another one with just 10 degrees. That's the final velocities. This is Vi, this is Vf. The turn takes 3.0 seconds. Delta t equals 3.0 seconds. Calculate the average acceleration of the car during the turn. A average equals delta V over delta t. Remember that delta V is equal to Vf minus Vi. So Vf minus Vi, this is equal to Vf plus negative Vi. So I need to, in my picture, I need to add in my negative Vi, which looks like this. Still, it's still 45 degrees. Okay, so my line is going down like this. We still have 45 degrees here. It's still the same magnitude. This is my negative Vi. Now the job is to add Vf plus negative Vi. Once you've got the result, which is our delta V, you can divide by delta t. So I'll leave that one for you to try on your own, and then during class time you'll have a chance to work on these homework problems. So enjoy those, give them a try, and I'll see you in the next lesson.